Morning, everyone, and welcome to today's live lecture, which is about modeling, dynamic modeling of robotic systems. Before I'm diving into that part, into the Piazza Q&As and the quizzes that we were doing, I want to give you some information about the exam, the midterm quizzes that we're doing tomorrow. We sent out everything already via email and through Piazza. Nonetheless, I want to quickly go over it, and if you have questions, just post them here in the chat. So this is the information that I sent out. The exam will start 8:15. It will be an exam that will take place here at ETH. So in contrast to the other exercise sessions, you will be here at ETH. It's 1 hour, 15 minutes. If you have done the exercises with MATLAB, then you're very well prepared. It's going to be very similar to this, which means bring your laptop, make sure that you have MATLAB installed. We will distribute the files at the beginning through Piazza. You will download it and then start immediately with the exams. Make sure that your laptops are charged. Nonetheless, if you have issues with the batteries, we're going to bring a couple of multiplugs. After you're done with the exam, you will have to upload all the files as one zip file to a folder that we will tell you or will give you a link for. And then the grade will be based on these results that we produce with these MATLAB files. The exam is open book, which means that you can use the script, slides, exercises, whatever you like. All what you're not allowed to is communicating with your colleagues or use internet. We have two rooms. One is in HG, in the G floor, and the other one is in EFV, so make sure that you go to the right room based on your surname. To answer the questions that are in here in this chat, first one, whether or not we can use internet for MATLAB documentation. You can use the helper function within MATLAB, but you just to like read about syntax or whatever, but you're not allowed to go beyond that. Can you access the lecture slides? You can access them through Piazza. In general, I would recommend you to download the slides anyway to have a local copy somewhere on your laptop. Then whether or not you're allowed to bring an iPad to read stuff aside. So many people in the meanwhile don't print out scripts and whatever. If you have this on an iPad or another tablet, that's okay for me if you have that on the side, as long as you're limiting it to lecture materials. For those who don't have tablets, can they use their mobiles? Yes, but I don't know what you would need the mobile for. What you have is a laptop in front of you, so you can also read stuff on your laptop. So you can use your laptop not only for MATLAB, you can also open the scripts and everything on your laptop. So I would really strongly recommend, if somehow possible, just stick to your laptop. Don't have tons of equipment around if not necessary. But if this is required, then of course you can. Can you use the functions that we implemented in previous MATLAB exercises? Like if you read the regulations, everything that we provided, that you made, can be used. It's open book, so you can copy paste things around. Is this clear? Are there any further questions that people have related to tomorrow's midterm exam? All right, if not, then we move on. We wanted to have this exam to be an exam which is on site, where everybody attends. However, it looks like there's some colleagues in your class who are affected by COVID, who are not allowed to come to ETH. So what we did is we changed the regulations last second, such that people that have reasonable proof why they should not come to ETH. If you are sick, if you are under quarantine, whatever, you're not coming to ETH, and you send us a proof beforehand until tomorrow morning, 8 a.m., we will approve this or not approve this, and then you can do the exam also from home. Exactly same rules as for the people that attend here. To be fair, you will not be able to use additional screens and desktop PCs or whatever, just you and your laptop on a table. What we want you to do in order to be able to check whether or not you had communication with additional people or are using internet, what we want you to do is that you either use a webcam or your mobile phone to take a video of yourself taking the exam, including audio, and you send this to us after the exam. Exam will be exactly the same time as the people doing it at ETH, so we will also have to submit it at the same time, and then 1 hour afterwards you have to send us this video to download. Are there any questions to that? So there's a question whether or not we can have a Zoom meeting for surveillance. We unfortunately cannot offer this for this specific midterm exam. We want you to record this yourself. I think it's a very reasonable effort. Put your smartphone somewhere on the side and record yourself and the laptop, and that's it. If you want to make a Zoom meeting yourself to record your screen, we still need to have somehow a webcam that gives you a third person view. We want to avoid that you use multiple screens just for the fairness with everyone. All right, if there's no more questions related to the exam for tomorrow, we're going to move on now with the couple of questions that are raised in Piazza. We'll go through them. So first one was related to the calculation of pseudo-inversions if we have a null space projection matrix in here. And the problem that was raised is that if we calculate the null space projection matrix using this formula, what you get is a matrix which in the end is ranked efficient. So also this thing very often is ranked efficient. And if you use the standard Moore-Penrose pseudo-inversion, that somehow isn't really numerically stable. There was a discussion ongoing in Piazza whether or not one can now use a damped pseudo-inversion in order to numerically stabilize this. So if you have the pseudo-inversion in the first manner, what you do is you have a minimization of the error in your actual task. Now, what is happening is if you add a damping term in here, is that you're changing the minimization problem to a minimization of the task error, but then also the variables that you're optimizing with. So in the end, you will not get the best solution in your subspace where you can do an optimization because you're kind of biasing this to a minimal X with this additional term in here. What you really want to do in the end is you only want to optimize in this reduced space that is limited through this n and only optimize these x's, which means you want to have a version of an optimization which essentially is cutting out that subspace that allows us to calculate also with ranked efficient solutions or things that are becoming close to be ranked efficient. So what one typically does is that we are using a pseudo-inverse function which can handle ranked efficiency. So essentially what it does, it ignores that part which produces this ranked efficiency and only inverts the rest. Or the second thing is that instead of using this this null space projection matrix that we have here, which creates an n by n matrix with a certain ranked efficiency, you calculate the null space projector, which is full rank. So for example, if you take the MATLAB function that we had typically used in the exercises. So if you take null of a J, what you get is a n by m matrix, which is full rank, but only to the portion of what is actually within this null space. And this is typically done using single value decomposition or QR decomposition. You don't have to do this at all by yourself. All you need to know is that in the implementation that you're doing, typically what you will do is you will both for your null spaces and for your pseudo-inversion, you will use toolboxes that are numerically stable, that are beyond the standard Moore-Penrose pseudo-inversion, and that null space protector matrix that have all of that embedded. The second set of questions, okay, there was one question to this. Can you describe what rank and column deficiency mean in the context of robot dynamics? All right. So let me show you this here. If let's look at this. If you have J1, which is a matrix that spans, for example, R2 times 4. So you have a task rank, which is 2, but you have 4 degrees of freedom that you can optimize with. That means for your lower priority task, you leave a null space, this N1, which has the dimensionality or the rank of 2. So it spans a space which is 2-dimensional that allows you to manipulate these degrees of freedom in 4 minus 2 dimensions without violating the task. But if you calculate this N here, this will be this N1 that you get from here. This is a 4 by 4 matrix, but it has only rank 2. If this J here, however, is 3 times 4, you have then a null space which is only 1-dimensional. You can only optimize Q in one further direction. So your 4 by 4 matrix has only rank 1. If I take the null operator of MATLAB or something else, where we go through the single value decomposition or the QR decomposition, what you will end up here is a N matrix N1, which looks like this. It has 1 dimension here, and it has 4 entries. And then the last question is whether or not you're requiring a specific MATLAB toolbox for the exam tomorrow. Like everything standard that we were using so far is what you require. There's nothing more. You don't have to install anything additional to that. For the sake of time, I have to move on here. Second questions on Piazza were related to what is the difference between task and end effector velocities. I kind of use these things interchangeably. Task for me is just much more generic than end effector, but an end effector velocity can be a task. So for example, if I'm describing a robot arm and I have a task description which says like, move my end effector with a certain velocity, then the task and end effector velocity are exactly the same. But there can be multiple tasks. One task can be move it with a certain end effector velocity. Another task can be make sure that joint 1 has a specific velocity. That's also a task, but it's not the end effector velocity, but it's joint space velocity, which means that the Jacobian that does the mapping between joint and task space becomes kind of a selection matrix at different units than if it's mapping to the end effector velocity, but it's the same situation, the same mapping between joint and task space. The second question was related to, or the third question was related to when is multi task control possible, under what conditions. In general, multitask control is possible if you have more degrees of freedom in your robot arm than degrees of freedom you want to fulfill in your task. That leaves you with like internal degrees of freedom that you can still optimize. You can make sure, for example, that another task is fulfilled, or you can make sure that you minimize your joint space velocity, things like that. But all of that is, in essence, another lower level optimization that you're doing to shape the solution of Q dot without actually changing the task that is achieved. For example, that an end effector trajectory and end effector velocity is tracked. And then the last one was related to what is the Jacobian now doing? We have looked at it always the following way. A Jacobi maps joint space velocities to task space velocities or to end effector velocities. It does not map joint space positions to end effector positions or to end effector orientations, because of the fact that in here, this is a nonlinear dependency. We have the position and orientation being a nonlinearly dependent function on Q. And J, in essence, is the linearization of F with respect to Q. In particular, if you're looking at the 2D space, it's a bit more tricky if you're looking at orientations with the SO3 space. And then the last one, there was a question like, why is RBP dot in B the velocity, not RBP in B the velocity? What is the difference between that? The difference is if you look at RBP from B frame, so in B, this is constant. So if you look at this over time, if you give a numerical expression for this vector, it's constant, which means if I take the time derivative of it, of a constant vector, it's going to be 0. However, there is a velocity at this point P. So if I'm expressing the velocity in frame B, then it's non-zero. And we have looked at this already earlier. Due to timing reasons, I will not go through this. Check out kinematics 2. There is a detailed slide which really elaborates this, and it's for a slightly different setup, but you can do the same in analogy also for the questions that are raised. With this, I would like to conclude the recap for the Piazza session and move on with the quiz that we were doing in this week. Very brief recap. What did we learn in these video segments? We learned the description of the equations of motion, so the description of the cause of motion. Input is a torque and output is a motion, an acceleration given to my system. And we always ended up with a description that looked the following way: mass times acceleration plus P plus G equals to actuation torque. And then you also had external forces which are mapped onto the system dynamics through the Jacobi transposed mapping. We learned different methods that all have their origin at the principle of virtual work in particles, which resulted in conservation of impulse and angular momentum. And we looked at 3 different methods. First one was Newton-Euler. So you essentially make a free cut of every single body of your multi-body system. You then do conservation of impulse, angular momentum for each of these body. You get rid of all the things you don't want to know and all the unknowns. And in the end, you have the equations of motion. The second we looked at was projected Newton-Euler, to do the same thing, but now only using generalized coordinates. And the third one is Lagrange 2. I will not ask you questions like you have to now go through all these 3 different methods for a certain example or whatever in an exam. But the key thing I want you to understand from this lecture is, in essence, that these three methods, they are pretty much the same thing. So we have seen many similarities. We have seen, for example, that it all boils down to a couple of Jacobians at the center of gravities, a couple of inertial parameters that you're needing either to set up the energy, to set up the impulse and angular momentum, to do then a free cut, or to do the same thing, but now in a joint space with a projected Newton Euler. What is important for you is that you kind of figure out your own preferences, depending on the problem, which solution is the best one for you to apply. I personally work quite often with projected Newton Euler because I find them very intuitive. If we add another segment or if we change the topology, it's pretty clear in what has to be changed, very straightforward. But in the end, it really doesn't matter. So whatever is most convenient for you. We also looked at the very end how we introduce external forces, so how this is mapped through the Jacobi transpose on the equations of motion. The important element here is that whatever you do, if you set up your equations of motion, if you then add another actuator or an external spring or something, you can always just manipulate your equations of motion by adding this external force and the Jacobi transposed at the point where this force is applying, and you get your updated equations of motion. So there's no need of like going back to Lagrange and introducing spring energy and then doing derivative of that, of the potential energy, and so on and so forth. You can directly map it through Jacobi transpose times these external forces. And then what we were doing is we ask you to go to like one example, but with these three different methods to find the equations of motion. So first one was free cut. We did here a free cut, which is essentially the most generic free cut you can think of. So we have contact constraints at the ground. So this is not allowed to move in y direction. Nonetheless, we completely free it, which you will see later on is not really necessary for this case, but this is the most generic approach you can do. For every connection you're separating, you need to introduce contact forces or reaction forces. So we have here in the middle a joint where we have force X and force Y of that one joint, and you have the action on the cart and the reaction on the pendulum, or vice versa. Contact is a rolling contact, frictionless, which means you can only produce normal forces here. Now what you have to do is set up impulse angular momentum for the cart, which means you look at the x direction. So you have mass times acceleration of the cart. So m times x double dot of the cart equals to this force. We have a forward pulling force, so it's positive. Then we do the same thing in y. We have the mass of the cart times the acceleration of the cart. Now we have forces of this joint and of the two contact wheels minus the gravity part that comes in from the mass. So minus this mass of the cart times gravity. And then the last element is that you look at it into the orientation. So we have orientation, we have the inertia times the angular acceleration, and we can now make this around the center of gravity. Important is always that you're doing this about the point where you define your inertia. So if you would do the angular momentum around that point, you have to make sure that you have either the inertia around that point or you take the mass offset, the Steiner Anteil of it as well. If you do it around the center of gravity, you just take the inertia of the cart. And then you have these two contributions by the forces. So you have this offset B times FR is positive, and you have this offset times FL, which is negative. The dimensionality of this theta for a planar system is one-dimensional because we are rotating only in one direction. If you're talking about the 3D system, then of course it's a 3x3 matrix. And also there, make sure that you always know around which point this inertia tensor was defined. So typically, if you open your CAD model, you have to set your origin to determine your inertia tensor, and then you have to also make the angular momentum at that point with the inertial tensor. Now you do the same thing also for the pendulum. In x direction, we have here mp times acceleration x direction is equal to minus fx. Then you do it in y. So you have here in y direction, here we have two forces, Fy and mpg, which point downward, so they have a negative sign both. And then we do the rotation of the pendulum. We have it around that point. So we have the inertia around this point times phi double dot square. This equals to all the external momentum. So we have momentum coming from this Fx times that lever arm, which is L cosine phi p, and then we have this Fy times that lever arm, which is Fy L sine phi. And the next thing you have to know is the kinematics. So we have two parameters or two configuration parameters that allow us to describe the complete state of the robot, namely x and phi. So what we need to express is the x of the cart, the y of the cart, and the orientation of the cart, and for the pendulum as a function of these two generalized coordinates. So we know that the x of the cart is equal to the generalized coordinate x. The y of the cart is 0 because you have a constraint there. Also, the rotation of the cart is 0 because of a constraint there. For the pendulum, it's a bit more tricky. If I look at x of that point here, what we have is this x plus that offset, which is the L sine phi. If I look at the pendulum, at y of the pendulum, we have 0 minus this offset, which is L cosine phi, and then the orientation of the pendulum is equal to my second generalized coordinate phi. Now what I end up here is, I have to do also the double differentiation to get the acceleration, but what I end up with is, in essence, 12 equations with 12 unknowns. The question is, like, what is in the end the dimensionality of the equations of motion? Now, the dimensionality of the equations of motion is determined by these generalized coordinates. So by a set of coordinates that completely describe the motion of the system, of coordinates that are non-redundant. So if I would use x of the cart and x of the pendulum and phi, then you would have a redundancy. So that's not the minimal set. Only if you choose one linear and one angle, this thing is becoming fully determined and minimal. Now what you have to do is you have to somehow manipulate all these equations here in order to get to the equations of motion. So I leave them here for clarity. And we start with like integrating them in here. So first thing is, first equation will stay. Second equation, we replace now this y double dot from here. We do the same thing for the x double dot here. Let me take a pen here. So we're looking at the x direction of the cart. We don't look at the y and rotation. Then we take this in here. We take this in here for the pendulum, and we have the rotation of the pendulum. Now what we can do is we see that we have here fx and here fx and nowhere else. And we're actually not interested in fx because this is a constraint force. So what we can do is we can combine these two equations and come up with this first line. So we see already the first line of the dynamics equations of motion. It's depending on acceleration, linear direction. It's depending on acceleration in rotation direction and on the state, so the position and the velocity. And then we can also insert 13 and 15 into 16. So we combine this one and this one into here to get rid of fx and fy, and you end up with a second line. So what we have here at the very end is a coupled two-dimensional equation of motion based on x double dot and phi double dot. So what I gave you here with the cart and the pendulum is probably the most simple system that one can think of. Already, if you have a double pendulum, this is getting crazily complex, and you will not be able to do this by hand. So you need mathematical tools to go through this. But you see the process, you set up a number of equations and you try to combine them linearly in order to get rid of the constraint forces and the the body description parameters, not the generalized coordinates, to end up with an equation which is only depending on generalized accelerations. Now we do the same thing also with projected Newton-Euler equations. What we have to do for this is that we start with the kinematics of the cart and of the pendulum. So what we do is we use the generalized coordinate x and phi, and we define what is the center of gravity position of the cart as a function of q. So we have ROS, so between the origin and the center of gravity of the cart, depending on q, which is x and 0. And this allows us then to calculate the Jacobian of that center of gravity and the time derivative of that Jacobian. We do the same thing also for the pendulum. So we have to determine what is the center of gravity position of the pendulum with respect to O, or in the inertial frame. What we have to do for this is we go by x in x direction plus L sine phi, that's that part, and we go minus L cosine phi in y direction. There is an offset here. There is an offset here, constant offset. However, that doesn't matter. So wherever you've defined the origin, it doesn't matter with respect to the height. If you do this, if you have this R, you can then calculate the position Jacobian of the pendulum and its time derivative. So just first line with respect to x equal to 1, first line with respect to phi equals to L cosine phi, for the second line with respect to phi, and then you do time derivative of that. Now the pendulum can also rotate, so you have to also define what is the angular velocity of the pendulum, which is phi dot. It's directly given by this generalized coordinate. So if I look at my rotation Jacobian, it has a 0 for x and a 1 for y. It's a 1 by 2 matrix. So with this, we have all the ingredients that we need to determine the equations of motion. So if I want to calculate the mass matrix, this is the formula we derived last time. We have Jacobi transposed M Jacobi for all the bodies, for all the center of gravities, and the same then also for the rotation, but here with the rotational tensor. Now we're talking about the planar system, which means that M is not the tensor. M is a scalar value, it's the mass, and also the inertia tensor is not a tensor, but it's only a one-dimensional scalar value. So let's do this first for the cart. The cart has only a linear contribution, so all I need is my JP times M, JP transpose times M times JP. And then this part is the part for the pendulum. First element is the position part, second element is the rotation part. So as you see, it's a number of Jacobian that we already determined there on top. You integrate them in here, and you will end up with this mass matrix. So the question here is how this rotational Jacobian is determined for a 2-degree of freedom system where we have like a definition of an angle. It's not SO3, so we have a direct definition of the angle by phi. We can do partial derivative of d phi after dq. We can also look at angular velocities and then do d angular velocities with respect to dq dot, because we know that there is a linear relationship, a linear mapping between q dot and angular velocity through the geometric Jacobian. The geometric Jacobian here is expressed with respect to inertial frame, as also phi dot is expressed with respect to inertial frame. So you need to have the absolute angular velocity here, not the relative angular velocity between one body and another body. All right, so coming back to the equations of motion, same thing for B. We have here this formula that we derived last time, where we have contributions coming from the mass with the coupling term J dot Q dot, from the inertia with J dot Q dot, and then we have this cross product term, which for a planar system is going to be 0. Now we know that for the cart we have that part Jp dot is 0. So this is essentially for the cart is 0. Also that part for the cart is 0. The only thing that remains then is, in essence, that we have to take the position of the pendulum times the mass times Jacobian time derivative of the position Jacobian times q dot. And if you do this, you will end up with this cross-coupling term. And then we do the same thing for gravity. We have here gravity equals to minus J transposed F for the gravity part of the cart and for the gravity part of the pendulum. So we add this, we sum this up here. We see that for the for the cart part, this contributes to 0, so there's not really part of it. So all what remains is the pendulum that we see down here, which gives then 0 minus GL sine phi. So to me, this is a very straightforward, very simple and clean way in how you can get the equations of motion. We did the same thing then also with Lagrange 2. With Lagrange 2, what you have to do is you look at the same kinematics of the cart and of the pendulum. So again, you start with center of gravity position and center of gravity velocities. For the pendulum, this is for the pendulum and for the cart, and then you determine the kinetic and potential energy. For the kinetic energy, first, what contributes is mass times acceleration of the cart, mass times acceleration of the pendulum. And this is the contribution in here are threefold. You have the pendulum part here, which is the velocity part, which goes in here. And then you have the phi part, which comes from the squared of this cosine. And then you have the coupling part, which gives you this. And then you have finally the contribution to the energy, which is coming from the rotational part. Then we do the same thing for the potential energy. Potential energy equals to just the mass times its height. And the height is given by L cosine phi. So we're looking at how high up this is. This can have an arbitrary 0 level, so you can add any additional potential energy. What happens is if you do partial differentiation of that, you get rid of, or time differentiation of that, you get rid of this constant choice of the level. So what you have to do is you have to then like use the Lagrange 2 equation, so time derivative of the partial derivative of kinetic energy with respect to velocity. First, that's the first contribution. Just take this line and like do partial differentiation with respect to x dot and with respect to phi dot. Second, you then do a time differentiation of this. So this is straightforward. Mx dot will become a x double dot, same for mpx dot. And then in here you have the product rule. So you have phi double dot, and you have the phi dot squared times L sine phi if you do the time derivative of cosine phi. And similarly also for the y direction. And you also do the partial differentiation of t with respect to dq. Should also be straightforward, and of u with respect to q. So all of that together will result finally in the same equations of motion that you have seen before. And as we see, like, we need the exact same things that we did previously. We need to have center of gravity, positions, and velocities. Now, instead of using that to determine Jacobians and directly going to the mass matrix, we're using these velocities to determine first kinetic energies and the position to determine potential energy, and then we do a differentiation to go to the equations of motion. But the ingredients for the whole procedure are more or less the same. Now, the last element which is important is how can we deal with external forces. I gave you a couple of examples in the video segments already. The thing that we looked at here is a motor that is directly attached to the cart. So what you need to look at is, what does that motor produce? It's a force acting on our system. So what we need to have is the Jacobi at that point where it acts upon to map this external force to the dynamics equations of motion. So let's do this. We look at the action of the cart. We calculate then the Jacobi at that point. So we know that the position we have r equal to x, right? The direction. So if you look at the Jacobi, this is dr dq, with q being x and phi. So we get the 1, 0 Jacobian. That means we have then the torque acting on our system, which is Jacobi transpose times f. So we have an f actuation x direction and a 0 in rotation direction. It's actually intuitively clear that this must be the solution, because this actuation force here is really acting directly in the direction of the chosen generalized coordinate. And that's also often a reason for how we select the generalized coordinates. If I have an actuator in a joint, I often select that degree of freedom to be a generalized coordinate of my system, because then I see directly that actuator in that line that corresponds to that generalized coordinate. I don't have to have any complex mapping in between. But even if you would choose different generalized coordinates to describe the system, you could still use this method to determine the Jacobian as a function of your generalized coordinates to see how your external forces or internal forces act on your system. With this, we're again done just in time. I will make a video of that, upload it again today. I wish you all the best for the exam tomorrow. Again, it's optional. It can only improve your grade, so no problem at all if you A, don't come, or B, if you don't do that well. And next session will then be about using these descriptions that we have here about the equations of motion in order to control our system. With this, I thank you a lot and wish you a good lunch. Bye-bye.